Okay, so today we're going to go over the periodic table, the interactive periodic table. So we're going to go over this. All right, so let's go over this. This was given last time. This is review because last time we did talk about the periodic table. So I want to go over this. Let's open the actual interactive periodic table. So hopefully you remember some of this stuff. Some of this stuff is new. Some of it is, a lot of it is actually just a review. So here's an interactive periodic table that I showed you last time. Okay, so we're going to use that to answer some of these questions. But some of them you might not even need a table. So let's just go through this, okay? So the first one is just looking at 4 groups. So group 1, group 2, 17, and 18. So if you remember, group 1 is the first column. So that would be this group. So group 1, they're called the alkali metals. So we're going to call them the alkali metals. Let me just put my pen on here. These are called the alkali metals. Group 2 is the second column, and they're called the alkaline metals. All right. Group 17 is the second last column. That would be this column right here. And if I click on that, they're called the halogens. And then the last group called the noble gases. Remember, those are the ones that are stable, the ones that everyone wants to be like. So if I look at group 1 in the periodic table, the first 3 members are hydrogen, lithium, and sodium. So hydrogen, lithium, and sodium. If I look at group 2, it's the first 3 members are beryllium, magnesium, and calcium. So Be, magnesium, and calcium. If I look at group 17, okay, so group 17, the halogens, it's fluorine, chlorine, and bromine. And if I look at the noble gases, the first three members are helium, neon, and argon. Okay. Now, if you remember, when you do the Bohr-Rutherford diagrams, there's a pattern. So if you look at the number of electrons in the outer shell, that's the outer shell. Remember, the row number determines the number of rings, but the column determines how many electrons in the outer shell. So if it's in column 1, it has 1 electron, or just 1. Okay, 1 electron. If it's in column 2, it has 2. This is, of course, 1 neutral. Okay, remember that, 1 neutral. The halogens have 7 electrons, and the noble gases have 8, except for helium, because helium can only have 2, because it only has 1 ring, and the first ring can hold a maximum of 2 electrons. If you remember, they want to be like the noble gases, because the noble gases are stable, so they're not reactive. The closer they are to being full or empty, the more reactive. So alkali metals are very reactive. Halogens are very reactive, but the alkalines are a little bit less, so we'll call them fairly reactive. Kind of like the group 16. Group 16 is 2 away from being full, so they're also considered fairly reactive. Okay. Any questions so far about just filling in the table? This is all review from last time. Second part is metals tab. So where are the metals located? So if we click on metals, you can see the metals are located to the left of that staircase. So we'll say that they're on the left side, and in the middle. Definitely not on the right side. Okay, so they're basically to the left of the staircase. I'm going to call it a staircase. Now, what are two properties of metals? It says that metals are shiny and they conduct heat and electricity very well. I know this is because we kind of covered this when we did the questions. Last time we met on Wednesday, we went over course outline questions. So a lot of this is repetition. So that's good reinforcement. So metals are good conductors of heat. So they conduct heat and electricity very well. So you can use them, for example, for cooking. You could use them to conduct electricity in your, wires are made of metal, obviously, because you want electricity to flow through them. If you look at nonmetals, nonmetals will therefore be on the right side, or we could say the right of that staircase. Nonmetals are on the right side. You can see there's that staircase. They're on the right side of that staircase. And what's true is the opposite, that they are not good conductors. Oops, not good conductors of heat and electricity. So that's kind of like the opposite. Okay. Okay, so just some stuff on periodic table, and a lot of this we already covered, so this should be review. What determines the order of elements? Okay, we should know this. It's a number of protons, right? Which is the atomic number. That's review, right? The periodic table was initially organized by mass, but then it was changed to reflect atomic number. So the fourth element in the table has 4 protons, right? The 14th element has 14. So that's how they're organized, by atomic number. What's the definition of mass number? Okay, we should know this. The mass number is equal to the number of protons and the number of neutrons. Now, what's the max number for magnesium? Okay, if we round it off, magnesium is about 24. That's magnesium. Potassium is about 39. And arsenic, can't remember arsenic, but arsenic would be, where's arsenic? Where is, right here, there's arsenic. So if we click on arsenic, its atomic mass is about 74.9, so I'm just going to say it's 75. Or round it up to 75. So arsenic is about 75. Okay. All right. Again, that should all be kind of review. Click on oxygen. Click on. Okay. So just to be a little bit quicker here. So oxygen. What is its biological role? So oxygen is used. If you remember, organisms need energy. We talked about flow of energy in ecology. So actually, oxygen is a very important ingredient in making energy from food. So when we eat stuff, oxygen actually helps convert the food into energy. It's a process called cellular respiration. To be more specific, it's called aerobic respiration, where the term aerobic means oxygen is required, because it can actually be done without oxygen, but we can't do that. So for us, we need oxygen to get energy from food. It's about 20. So the numbers are about 20 to 21% of the air is oxygen. Okay, so that's the percentage of oxygen in our atmosphere. If you look at nitrogen, nitrogen is actually the highest. It's about 78 to 79%. And its use is in building certain very important molecules in our body, like protein and things like DNA, which I'm pretty sure you've heard of that. Okay, so these are very, very important molecules in our body that require nitrogen to build it. Okay, click on element 90. What is it named after? So those of you who are Marvel heroes should know this one. So element number 90, we go back to periodic table. Where's number 90 here? Number 90 is right here. Number 90 is thorium. Yes, named after the Greek, I was going to say Greek god, Scandinavian god Thor. So the answer to that question is named after Scandinavian god Thor. You know, you remember Thor from your Marvel superheroes. Click on AU. So AU is, go back to the periodic table. All right, where's AU? AU is right here. AU is number 79. It's gold. So now why is it AU? Because sometimes we don't use the English name. You know, we might use different languages. So this is an old Latin term. So aurum, which stands for gold. So sometimes the Latin or maybe another language is used to, just, you know, to come up with that symbol. So this is gold, and it's the Latin name for gold. That's why I said this is a little bit tricky with the symbols. Okay, density is an interesting one. Well, actually, it's our next topic because the next time we meet, we're going to talk about properties of matter. We're going to do a focus on density. So density is actually described, I'll just make a little note here, as the amount. So, you know, you're familiar with, like, you know, weighing something, you put something on the scale. So density is the amount, usually it's like some, you know, like maybe grams per volume. And it could be something like this. The amount of grams per volume is the density of a substance. So it's not as weight, it's basically the amount of weight, and weight is actually not the right term, it's actually the amount of mass. It's not really the term we should be using. It's the amount of mass per unit of volume. That's the density. Things like gases have very low density. So for example, go back to the periodic table and we click on something like helium, all right? So if we look at helium, its density is very tiny. It's like, you can see it's like 0.000164 grams per centimeter cube. Because helium is a gas. Gas, you know, they don't have a lot of mass in a particular unit of volume. But if I look at, for example, something like in the middle, like for instance, like iron, okay, here's iron, Fe is iron. You can see iron has a density of about 7.87 grams per centimeter cube. It's like maybe about 1,000 or 10,000 times bigger than the previous number, because I can't exactly remember what the previous number was. But the metals, which are in the middle of the table and on the left side, those are the areas of highest density. So there's actually a little thing we can click on here where it says trends. So click on trends and you see where's the density. All right, so you can see that the little bars here represent areas of highest density. So you can see it's actually peaks kind of in the middle, and then it drops off as we go this way. You can see like things like the gases on the right side, like they have almost like no bar because their density is almost like zero. It's not zero, but it's like you can see here, neon, 0.000825, whereas carbon is 3. As a dense, that's when it's in the diamond form. Aluminum is 2.7. Iron is 7.87. Osmium is the highest. So centimeter cube is like a milliliter. So a milliliter of water, like maybe a drop of water, would have about 22.6 grams of osmium in it. So if we look at the question, where are the most dense elements, they would be in the middle. If you look at the trend. And the most dense is something called osmium. And its symbol is OS. And it's about, what was it, 20, what did I say it was? 22.6, so round that up about that. Grams per centimeter cubes. Okay, that's the most dense. Okay, we're almost done. We have one last question. We're going to look at aluminum, samarium, helium, and neptunium. And we're going to look at their symbols. Okay, really cool. That's why I wanted to do this periodic table, because it actually looks very pretty. So if we go back to just the periodic table and we click on, what was the first one again? First one was aluminum. Okay, so aluminum is Al, and it has, you'll notice it has the symbol of an airplane. All right, now why is that the case? So go see right there, symbol airplane. So symbol is an airplane, and that's just to represent that aluminum is a very, very valuable metal, and it's used in lots of things. And it's obviously used in airplane manufacturing. Very important element in making airplanes. It's aluminum, so it has the symbol of an airplane. If I look at samarium, so samarium is, oh, there we go, samarium. Oh, samarium is interesting. So samarium has a symbol. I don't know if you can see that. Maybe, I don't know if this will make it bigger. Would that be bigger? Let's see. Okay, so this symbol, you see a sickle and a hammer and a star, and you see all those rays. Okay, so the sickle, hammer, and star is a symbol. So I'm just going to write sickle, hammer, star, and all those rays. See all the rays in this image? All these lines represent rays of light. So the reason for the sickle, hammer, and star is because that is actually the symbol for the Soviet Union, which I don't know if you're familiar with, but that was actually on their flag. So because this is the area, it was discovered in Russia. So before current modern day Russia was part of what's called the Soviet Union, and their flag had the sickle, hammer, and the star. So that if you look up Soviet Union flag, you will see that the sickle, hammer, and star. And the rays represent that it's used in lasers. So it's a very important element in making lasers work. If I look at helium, so if I go back to periodic table, zoom out a little bit. Helium is, you see it's the picture of the sun. It's actually named after the sun. So the Greek helios, meaning sun. So the symbol is the sun, because actually that's where it was detected. It was actually first detected in the sun. The sun is mostly hydrogen and helium. And our last one is Neptunium, which you might probably guess why it's named Neptunium. So where's Neptunium? Neptunium, where are you? There we go, number 93. So Neptunium has the symbol, the trident symbol. It says it was named after the planet Neptune. Okay, so it's a trident. All right, so this is you can see a trident. That's a trident. Trident is a weapon, but it says it's named after the planet. But oops, if you remember, the planet Neptune was named after the god Neptune. Remember, Earth is the only planet that's not named after a god in our solar system. So you can, I guess, say that Neptunium is indirectly named after the god Neptune. Okay, so this is the answer key for the interactive periodic table. I will post this. I will post this after the lesson, so that way, if you didn't get a chance to, do it or follow along, that's fine. Don't worry. I will post this so you can go through it if you have any questions. Okay. Any questions at this point? Because then what we're going to do is we're going to turn our attention now to this sheet, which is called classification of matter. This sheet, again, we're going to do this together. So you can just follow along, and then I will just simply post this. Okay. So we're going to look at how matter is classified. We know that matter is made up of little particles. We talked about the particle theory and the atomic theory. But now we're going to try to understand the different types of classification of matter. Okay? So here's a little chart to really help visualize this. And again, a lot of this is actually just a review because we talked already about the difference between some of these things. For example, we said what an element is, right? We talked about an element is something that is made up of a particular particle, one type of particle, right? So for example, if I look at, like aluminum, let's imagine this is the element aluminum. The element aluminum would only be made up of one type of particle, right? Not two types, one type. Now, remember, they could have different masses because you could have isotopes of a particular element, but they would all have the same atomic number. So we can say it's the same particle. A compound would have two types of atoms or more. So for example, if this was, well, I can see it's actually got two, and so maybe this is water. I don't know if it's water. Let's just say it is water. So water would be made up of two things, right? Water and oxygen atoms. Now, these are called pure substances because what they both have in common is they both have one type of particle. Okay? If you look at elements and compounds, there's only one type of particle that makes up the element or the compound. Now, we can contrast that to what's called a mixture. So a mixture, if I look here at what a mixture is, you can see in both these examples that you have two or more types of particles. So for example, I can see I don't know what color that is, fuchsia, and I can see green. These are clearly two different types of particles that are not stuck together. So not like this example over here where these particles, they're made up of two different atoms, but you can see they form one type of particle. Because I can see that this one and this one are exactly the same. But here I can see two different types of particles. And I can see the same thing over here. So here's one type of particle, and I can see this is a different type of particle. So these are called mixtures. So they're not pure substances. We can talk about a way to classify mixtures. We can use a term. We can say it's either homogeneous, right here, or heterogeneous. So what that means is if the mixture is made up of two or more particles, but it looks like it's just one thing. So for example, if I have a glass, let's say of salt water, okay? I'm going to call it salt water. Well, what is it made up of? Well, if it's salt water, right? So it's made up of two things. It's definitely made up of water. So it's going to be made up of water particles. But it's also going to be made up of salt particles. Two different types of particles. But when you look at a glass of salt water, you only see one thing. It looks the same, right? Every little section of this glass would look exactly the same, right? That would mean it's homogeneous. So when something is homogeneous, it means, it means it looks the same everywhere. Now, if you look at this picture over here, you notice that, it doesn't look the same everywhere. I can see like, this is like, I think this would be like a section of sand. I could see like different colors of sand grains, right? So this would be an example of something that is heterogeneous. As you can clearly see the difference between the two. So if homogeneous means everything looks the same, then that must mean, because elements and compounds are made up of one type of particle, these must also be homogeneous. Because every aluminum atom is going to look the same, every water molecule is going to look the same. So if I have a piece of aluminum foil or a glass of water, it's going to look the same everywhere, so we can say it's homogeneous. But if I have a mixture, let's say of sand and water, it's obviously not going to look the same everywhere. So then I could say that that is heterogeneous. Okay, so we're going to use some of this terminology, all right? So here's a little flow chart to help us understand this classification a little bit more. So it says we know we can divide matter into two categories, pure substances and mixtures. So here's another way to look at it with questions. So can we physically separate the matter? Okay. If the answer is yes, then it's called a mixture. Now, what does that mean? Okay, I'm going to explain that. So let's say, for example, actually let's look at the opposite. So if I can't physically separate that, then that would mean it's a pure substance. So what is meant by, let's go back then. What's meant by physically separating out something? So chemical separation is using some sort of a chemical reaction where what we're doing is we're rearranging the atoms. That's what's known as a chemical separation. So that would be, not an example of physical separation, because the definition of a chemical separation is different than physical separation. What you're doing so I'm going to come back to that, okay? What physical separation means is that you don't rearrange the atoms. The opposite. So what does that mean? So let's look at, like, for example, here is something called filtering. Okay, so what happens in filtering? Well, imagine that you have a piece of filter paper. Look at this. Now, you can't see this, but the filter paper has little holes. All right, little holes. And what happens is you make, you can see, like, you usually turn it into some sort of a shape. You can see the shape here. And you put it in a funnel, and then you pour something into the filter paper. This is how you make coffee, for example, okay? So what happens is, if let's say you have a solution that's made up of two things, okay, two types of particles, all right? Let's say one type of particle is water, all right? And water is really small. And maybe there's another type of particle, maybe like something like copper, okay? And that's really big. Now, what happens is when you put it through the filter paper, the copper would get stuck because it can't fit through the holes, but the water is small enough that it would just go right through. So the water would go right through the holes. But the copper is too big, so it would get stuck. Maybe the copper particles, maybe they're like flakes of copper or something, I don't know. and it's really, really big, and it can't fit through the hole, so it would actually get stuck as a residue. Now, we're not rearranging the atoms. You're not taking apart the water molecules. You're not taking apart the copper atoms, not doing anything. You're just physically separating them. So if we compare that to chemical separation, this is what happens in this case. This is something called electrolysis. All right. You take water and you put electricity through it. So what happens is when you do that, the water will split into hydrogen and oxygen. You can see that here. There's hydrogen and there's oxygen. Now, in that case, we've rearranged the atoms. The atoms would have looked like this. So water actually looks like this. Hydrogen actually looks like this. Hydrogen is actually an atom, but it's in pairs. And oxygen looks like this. So you'll notice that, if we look at the left side, the water molecule, when we compare it to the hydrogen and oxygen, the atoms have been completely rearranged. That's a chemical reaction. So when it comes to this, we can say we have mixtures and we have pure substances. Mixtures can be physically separated, but not pure substances. So if we put a pure substance through filter paper, it's not going to separate the pure substance. The only way you can separate a pure substance is through some sort of a chemical reaction by rearranging the atoms. So then on the left side, if we look at mixtures, we can physically separate them through filtering is one. Here's another example. This is called distillation. In this case here, we take something like salt water and we heat it. Now this would work with coffee too. Coffee is a mixture of coffee and water. This will work with water and alcohol. The way it works is you have two or more things, we'll just say two things, that have different boiling points. That's the temperature at which something boils. So you have the salt in this case, and then you have the water. All right. Now, water will boil at 100 degrees Celsius, but not salt. Salt, it heats way more than 100 degrees to boil. So at 100 degrees, salt, so at 100 degrees, salt doesn't boil. Okay, so what does that mean? So if I take salt water, let's imagine I have a beaker. Here's my beaker. And I have the two particles in there, okay? I have salt and I have water. Now, the water will boil. So if I heat this to 100 degrees Celsius, so it starts boiling, okay? I have a thermometer, check temperature. It goes to 100 degrees. What happens is the water will boil, okay? It'll literally start evaporating. So what happens then is the water will evaporate and it will basically go through this little tube. And as it cools down, it comes back into water again. So you can see that not changing the water particle, we're just converting it from a liquid into a gas. So, a particle of liquid water and a particle of steam, same particle. They're both H2O. But what happens is when we heat it, the steam rises and then it goes through this tube and then it comes back and cools back into liquid, but the particle is still the same. It's still H2O. So what happens though is that the salt will remain behind. So if we take off all the water and all the water evaporates, what you'd be left with is at the bottom, you'll be left with just salt, like little salt residue. So this is another way to physically separate mixtures. Again, we're not rearranging the atoms. We're just using a technique to somehow pull apart the two different types of particles. There is a third example, which I'm going to mention in a second, okay? Any questions about how to physically separate through filtering or distillation? So we're on mixtures. So we said mixtures can be physically separated. Now, going back to the previous example, we said that we can look at mixtures as homogeneous or heterogeneous, right? And that's what this means. Is the composition uniform? Yes means it's homogeneous. Okay, that's what that means. It's homogeneous, all right? So we know if it's homogeneous, that means it looks all the same, right? Everywhere. So we know that pure substances are homogeneous. We talked about that. They all look the same. Okay, so a homogeneous mixture is called a solution. If it's not homogeneous, that means it's heterogeneous. That means it looks different. One part looks different, another different part, right? Like sand and water would be heterogeneous. So that is called a mechanical mixture. So we can classify mixtures as solutions or mechanical mixtures. Mechanical mixtures are things where you can clearly see that it's not the same everywhere. So a good example will be like oil and water. If I put oil and water together, what you will see is you will see a beaker, you will see water, but on top of the water, you will see some oil. You can clearly see that there would be water and oil. You could tell the difference between the two. So that would be an example of a mechanical mixture. Whereas a solution, like with the example before, if I have a beaker of salt water would look the same everywhere. So it would be homogeneous. So mechanical mixture is something where we can see more than one type of substance. We can actually divide mechanical mixtures into two other categories. We can call them suspensions and colloids. So I'm going to explain what those two are. Okay. So once again, remember, physically separating things, we can only physically separate mixtures, not pure substances. So now we just classified mixtures as basically three types of mixtures: solutions, and then mechanical mixtures that are either going to be suspensions or colloids, okay? So we're going to look at these three. We're going to look at solutions, suspensions, and colloids, which are examples of mechanical mixtures, all right? So how do we distinguish the three? Okay, so a solution, we said, is something you can't, everything looks the same. We said it's homogeneous. Okay, here are some examples. We talked about salt and water or salt water. Air, interestingly enough, is also a solution. Air is a solution of, from the previous worksheet, we know it's got oxygen in it, and we know it's got nitrogen in it. And you should also know it has carbon dioxide. So because we often think of solutions as liquids, but not necessarily. Solutions can be gases too. And if I look at air, it doesn't matter if I turn my head left, right, up, or down, air looks the same. So it's homogeneous. But a suspension is where you can see different particles with your eye, like we talked about oil and water, or maybe mixing flour and water. A colloid is, it's a little bit harder to see that there are actually different particles in it. Maybe you might need a microscope. Like for example, milk. If I look at a glass of milk or paint, it would look like it's homogeneous. It would look like it's exactly the same. But there is a thing that we can do with suspensions and colloids, two things actually, that allow us to determine that they are mechanical mixtures and not solutions. The first is something called the Tyndall effect. Now, it sounds like Tyndall, our neighbor, our landlords, but it's spelled a little bit, I think it's spelled different. Actually, I don't know. Maybe it's spelled the same. No, I think it's different. Okay, so one is to put light through it. If we shine light through a solution, nothing happens. The light goes right through. But if you shine light through a colloid or suspension, you will see something. You actually see two things. One is you will actually see the light beam. So you can actually see the light beam. You see the beam of light here and here. Whereas if I look at my example with just water, I don't see the light beam. Okay. The other thing that might happen is, which actually will happen, is the light will actually scatter. So the beam will change direction. That's called the Tyndale effect. So it's called the scattering of light by particles. So colloids and suspensions will do this. Solutions won't. Another thing that we could use to, to distinguish solutions from colloids and suspensions is we can centrifuge them. This is when you put them in a little, it's a machine that spins really, really fast. You can see the machine right here. So it would actually spin really, really quickly. And what happens is, because these are mixtures that contain more than one type of particle, two or more types of particles, the way it works is the particles will separate because they have like maybe densities different or size is different. So what happens then as you spin them, the things that are less dense will rise to the top. So if I look at, for example, over here with my milk, this is milk that's been separated. You can see that there's a section on top. You see this band on top right here. There's my cream. And then you can see the skim milk, the plasma phase is obviously, you can see it's been physically separated. The milk doesn't look like that, but we can separate the milk into different components. We can do the same thing with blood. So this is actually a sample of blood. So blood is also an example of a colloid. So if we spin blood, you will actually see different layers. You can see 1, 2, at least 3 layers in the blood. And that's because there are different particles in the blood, and when we spin it really rapidly, they will separate. Now, solutions don't do this. So the centrifuge doesn't work with solutions. You can see it's working on colloids and suspensions. So if we did this with a mixture of oil and water, it would do the same thing, okay? But it won't work with salt water. Okay, so I do want to mention one other type of solution because I actually skipped over it, was alloys. So I mentioned that solutions, we often think of solutions as things with water, but air is a solution. And an alloy is actually a pretty interesting type of solution. These are metal solutions, so solid solutions basically. So this is bronze. Okay, bronze You're a history buff, you might have heard of the Bronze Age. Okay, bronze is a combination of tin and copper. So it's a solution of tin and copper. This is something called electrum. And this is a combination of gold and silver. So you can see that alloys are basically solutions of metals. This is steel. Steel is generally a solution of carbon and iron. So alloys are another example of solutions, okay? All right, so then to wrap up, so we can physically separate mixtures. We distinguish between solutions and mechanical mixtures. So then on the right side are things that we cannot physically separate. In other words, we can't use stuff like a centrifuge or distillation or filtering. It doesn't work. On the right side, the only way you're going to separate compounds is through some sort of a chemical process. So we can't physically separate them. But if we can chemically separate them, so there's this example here with chemical separation. So can it be chemically decomposed or separated? Then that would mean it's a compound. And if it can't, it's an element. So that means that if we can take the compound, the word decompose means to break it apart. Then if we can break it up using some sort of a chemical reaction, then it's a compound. So for instance, going back to this is water. Water is a compound. It's made up of two or more elements. We can chemically separate the water into its components. We can't do that with hydrogen because hydrogen, I spelled hydrogen wrong. Because hydrogen is an element. So if we can break up the compound, so if we can break up the particle, I should say particle. If we can break up the particle, then it's a compound. If we can't break up the particle through some sort of a chemical reaction, then it's an element. And that is it for classification of matter. The next time, we will talk about the properties of matter. Okay? So let me actually stop the record button. Hold on. Stop recording.